Good morning, Samantha. Please check my emails and tell me what should I do tomorrow. So we all know that if we want to build a virtual personal assistant like the movie Her, we need some services. For example, that robot or that AI assistant should provide speech recognition, should convert text to speech, and we should change the voice of Samantha. For example, it becomes a man or one of your close friends or one of your, for example, becomes your mother or your girlfriend. And intent classification, for example, we want to understand the intent of that text. And named entity recognition, we want to translate it to many languages. We want to summarize that and many other capabilities. So today we only focus on speech recognition. And there are many ways to do speech recognition, but nowadays we use CTC loss. So first we review CTC, then we review transformers, and then review wave-to-vec, which is one of the most successful algorithm for speech to text, and speech recognition implementation. I will provide the codes in my GitHub. This is my GitHub deep learning projects. So at the end of each lecture, you can see my codes in Google in my GitHub repositories, and so you can generate your virtual personal assistant hopefully by the end of this playlist. So we go through the theory and then the application. What is short-time Fourier transform? We do it usually in order to create some features. For example, I created this MP3 file, deep learning engineer. I said, I'm a deep learning engineer. And then I load it and I use LibRosa library. And so we have the file, and then we can just apply the short-time Fourier transform. This stands for short-term Fourier transform. And then we get using LibRosa, as I said, you can convert the amplitude to decibel. And so this is my voice when I say I'm a deep learning engineer. And so what is CTC? That is very popular these days. We use it as a good loss for alignment purposes. So connection is temporal classification. Labeling unsegmented sequence data with recurrent neural networks. So the goal is to train recurrent neural networks or anything. You can use even dilated convolutions. You can use transformers. You can use your favorite sequence-to-sequence model. And then we train it to label unsegmented sequences directly. And the idea is we want to interpret the network output as a probability label sequence conditioned on a given input sequence. For example, you provide, for example, you say the sound of, and then you have this waveform. So Z is the finite alphabet of labels, and you have the input. Your input is m-dimensional. So your input is m-dimensional, and when we say a temporal classifier, it means we want to convert sequence to sequence. And we have a label error rate for that. And ED is the edit distance, which is the minimum number of operations required to transform one string into the other. You can use this methodology for handwriting recognition as well, but today's focus is only on speech recognition. The reason that I put handwriting recognition and speech recognition together because the same technique could be used for similar problems. So here, for example, we use backward layer of LSTM and forward layer, and finally softmax, and typically we use CTC output loss. And so here we use CNN, and first we do convolutional neural networks to get some good representation, and you could use wavelet scattering, as I said in the previous playlist, and then you can use recurrent neural networks, but here you can use transformer as well. You can use dilated convolutions as well. Anything that is like sequence to sequence. Of course, we typically use RNN and transformer. Nowadays, we use transformer. So we have an audio, raw audio, and then, of course, you can implement it in SageMaker as well. It's very easy nowadays, but SageMaker, it is still in its infancy, but I really love SageMaker. But you can do everything from scratch if you like and use Python libraries like I do most of the times. So first you get features by the convolutional neural networks, and then you get tokens from the transformer, and that's enough for the CTC loss to say what is the transcription by changing the weights of the model. And in recurrent neural networks, so the total loss, this is the most important thing that you should care, because you can start a sequence, you can have a sequence, and at any time you have a different token. And for example, at each point you have a softmax to say, okay, this one is like, this is the probability to be some other thing. So at each instance of time until the final time, Tx, we can have this representation. And so we just use recurrent neural networks to provide to provide these probabilities, and then we use these probabilities. As you see, the probability is constructed by alpha, and alpha and beta are just created by the output of your neural networks. What is this one? This is the output for a given input. For example, you give Siri, hey Siri. Nothing. So, for example,
just a sec.
So, for example, so when you say this, it creates the probabilities at any instance of time. And deep search is deep search in 2014 is a very great article that we use, and I've implemented.
Sorry, I'm having trouble hearing you.
A similar algorithm, and it is in my GitHub. And the deep speech too, of course, I implement deep speech too, because first we need convolutions and then GRU unit, or you could use bidirectional. I used bidirectional recurrent neural network. And we have a look at convolution and fully connected, and the CTC loss can capture, can change the weights in order to provide the text. And so here we give the inputs, you have some output that using these representations, it creates and it understands the probability. And once it knows the probabilities, for example, it says that this token has highest probability. At the next time, this token is the highest probability. At the next time, until the last time. And the total probabilities is this is the product of all probabilities at time because they are independent. For example, at time 1, the probability of observing a label it is independent of the probability of observing that label at the next time. And this is my code. First we create speech recognition model, and it is inherited from an module, and then because of inheritance we use super because we want to just copy of the speech recognition model, and then residual CNN layers with filter size of 32. And here is our classifier. So we give the linear layer and then drop out and then linear. And here you see that we use fully connected bidirectional RNN and finally our classifier. So exactly similar to the paper Deep Speech 2. And this is like for decoding because it's a little bit mismatch between, well, everything in training, everything is differential, beautiful, but we should still work on the decoding because that's why people try to develop graph transformers in order to have a better approach for decoding as well. And the greedy decoder is, I use the greedy approach. And so finally, we have the probability of your label given your input X. And the B operator, what it does, it says, for example, if I say cat is the same as cat is the same as cat, so all of them is mapped to a single point. And we construct the classifier, and after that we train the network. So we have alpha and beta. The algorithm is very simple because we use the recurrence of dynamic programming. So we don't need to calculate that all of them is just a recurrence relationship, and we can calculate alpha and beta. And once we have alpha and beta, we can create this sequence. But the loss is accumulated over time, so we should add them up. And the maximum likelihood training, as usual, it should be differentiable like this. And you notice that this has a beautiful form because this form can be computed here. Here you can use this relationship in order to obtain probability of label given your input. And the error, this is a good measure for error signal, and we use it during training. And hopefully, and luckily, CTC loss is implemented in PyTorch. So you don't need to worry about the construction and debugging of those things because it's very critical if it has a bug. But if you use just the PyTorch CTC loss here, then you don't need to worry about the bug. So please use this one instead of implement it yourself because you won't want to invent the wheel again. And here we use, depending on the learning rate, you can optimize that. And finally, for different, for example, for 10 epochs, you can train and test that. So the parameters, hyperparameters that you need is number of convolutional neural networks, number of recurrent neural networks, number of classes, and dropouts, and all of those things. Stride. And Wave 2 Vec 2 is an improvement. So in speech recognition, it's very similar to the work of CPC. Contrastive predictive coding, if you read the paper, and it uses mutual information theoretically and then implement that. It's very beautiful. So you might think that it's very similar to that. But they are not the same thing. A framework, Wave 2 Vec, as it says, it's a framework for self-supervised learning of speech representation. And in speech recognition, labeled data is much harder. So the motivation for them is because labeled data is much harder to come than unlabeled data. It's much more expensive. And the current speech recognition system requires thousands of transcribed speech to reach acceptable performance, which is not available for the vast majority of nearly 7,000 languages spoken worldwide. So infants learned language by listening to adults. And this paper shows that only 10 minutes of labeled data, it achieves a word error rate of 4.8, which is great. And it is a clean test. Clean is better because, and we are using Libri speech data set, by the way. And so we pre-train, as usual, like everything, like BERT, like everything. We pre-train and then fine-tune. It's a good paradigm nowadays, isn't it? So pre-training using transformer with many unlabeled data, and then we use fine-tuning using CTC. You can use it for many articles, many algorithms. So the features, we get tokens by the transformer, and as usual, and you can use CTC loss for that. So Wave 2 Vec 2. So here we give just a few minutes of labeled data. So this provides a good representation here, and another good point in this article, it uses quantization. Of course, it has its own problems. So we fine-tune using CTC after pre-training. So we learn discrete units. And because of this, we use Gumbel. Gumbel, I think, is written here. Gumbel. And latent speech. And so we mask as usual, but here we quantize because we need it for the loss. And for quantization, I can say you have a couple of code books, and because for any group we have a code book, but we have G code books, not just one. And we discretize Z, which is a continuous variable, to get Q, which is discrete, like the one I told you in one of the lectures, semantic hashing using mutual information. That paper that I explained is very similar has a similar motivation as this paper. Because if you have discrete, first of all, you can use all discrete mathematics capabilities that you know in computer science and mathematics. And second of all, it's good for generalization. People don't talk about the generalization. I don't know why. This is one of the most important motivations for quantization. And here we use we calculate the probability of choosing with codebook entry. With codebook, but for group G. And tau is the non-negative temperature as usual. What is more important is that we add a noise. What is N? N is the Gumbel noise. I've not written here. It's here.